views. Which one are you seeing? Are you seeing the
Presenter view.
presenter view? Okay, let me swap that. Oh, yikes. What are you seeing?
We're seeing a very exciting image.
Is it
Lots
like-
of phase. It looks like a INSAR image where the phase is not very coherent.
Yeah, I was gonna guess LiDAR or something.
Made LiDAR.
All right. Let me see if I can fix this. We. All right.
Try stop sharing and share again and see if that resets it.
I have this problem with this monitor, so let me see if I can. Sometimes you can get the slideshow to show up on the. Let's see here.
If you go to slideshow options and pick whatever the middle button is in slideshow setup. Yeah.
Let me see if this fixes it.
Jacob, I haven't let everybody in from the waiting room yet. That's why she can't get in.
Does that look better? Or are you still seeing the presenter view?
It's still presenter.
Let me swap it.
Nope.
Should have sorted this out before. What's going on? Uh-oh. We will just do this. I will get rid of my monitor and put it on my computer for now. All right. That way there won't be any presenter view. Okay. Does that look good?
Yep.
Perfect.
All right. So, Todd, are we good, or are we still waiting?
I think all the committee is here, right? So I think we can go ahead and get going.
All right. Let in the flood.
Is Mom here?
Oh, is
Yes,
Mo-
I'm here.
Okay, good.
He's hiding off the side of the screen somewhere.
There you go. Just want to double
What are
check.
the rules? Do we have to be on video for? How does this work?
When we used to have rules on who knows if they're still in place during the defense, yes, we have to be on video, but not this part.
Okay, understood.
But I don't know that the rules really exist anymore.
Okay, well, I guess people are filtering in. Give everybody a second to settle in for the defense. First of all, I'd like to welcome everybody who's come. I know we have a whole bunch of people here who might not necessarily be used to attending the Maryland defense, some guests and other folks that are with us. So I just want to welcome you all, first of all. So today we're going to be hearing the PhD defense from Ernie Bell, who's been working with me for the past 5-6 years. I'll go through the introductory slides here, but there's some procedure that we have to follow. Okay. So I can make the slides advance. Our agenda for today is I'll go through some introductions. I have to introduce the committee and whatnot. That'll be followed by presentation by Ernie over Zoom for the approximately 45 minutes. Everybody here should be muted. Please, if you can unmute yourself, don't. And hold your questions for the end. There will be an opportunity to ask questions at the end of the defense. We give approximately 15 minutes for that session. go a little bit longer depending upon interest. If you want to ask a question, just use the Zoom option to raise your hand. There's a little instruction there about how you find that in the ribbon at the bottom. And then I will call on individual participants and unmute them so that you can ask your question. So after the public question session, we'll adjourn to a private discussion with the committee with Ernie. So the members of the committee who I'll introduce here in a second will talk with Ernie, and then we will adjourn. So that's the agenda for today. It's my duty to introduce the dissertation committee. I'm the chair, Dr. Nicholas Schmer. We're joined by Jessica Sunshine from the Department of Astronomy, who's serving as the Dean's Rep for this committee. Jacob Bleacher, who's coming over from Goddard Space Flight Center headquarters at NASA, who's on part of the committee. Menghan Huang, who's also a professor in the Department of Geology. And then Vedran Lekic, who's also a professor in the Department of Geology here in Maryland. So that's our committee who's going to be serving today. It's my pleasure to introduce our candidate, Ernie Bell. Ernie comes to us from a very colorful background of things that he's done before becoming a graduate student here at Maryland. He got a bachelor's in mechanical engineering at Penn State, followed by some time as a test facility operations engineer at NASA Glenn. And then he went on to get a master's in science and mechanical engineering at Carnegie Mellon, and then worked as a space station systems engineer, integration engineer at NASA. He also earned a master's in aeronautical space at Embry-Riddle University. During that time, he was also working as a NASA space station and space shuttle flight controller, an astronaut trainer at Johnson Space Center. And during that time, working in this sort of other realm, he had an opportunity to be a part of this desert rats, desert research and technology studies, and got interested in the geosciences and going back and getting a science degree. So that's who came to us at Maryland. So Ernie joined us at Maryland in 2015, and he's been here doing lots of great things since. So I want to go through some of his academic accomplishments and some of the things that he's done while here. He's a co-author on a paper in the Journal of Geophysical Research, Planets, and he has several other manuscripts that are in preparation. So he's been quite productive. He's been the lead on numerous abstracts to a wide variety of conferences and workshops. And he was a recipient of the Geologic Society of America travel grant for the Cordilleran section meeting. Ernie is an Ann Wiley Dissertation Fellowship recipient. And he's also been active in helping to organize meetings at AGU and putting together sessions, and has served as executive secretary on several NASA panels. Ernie is quite prolific in giving talks about what he does. It's actually quite interesting to students, and they like to hear about some of the planetary science that he's done. So he's offered lectures in various courses on campus, and he also served as a teaching assistant in the Department of Geology. So thank you for that service, Ernie. I think everybody here appreciates your contributions. So Ernie's PhD research is basically focused around using volcanic and tectonic terrestrial environmental analogs for understanding basically the science and operations of geophysical exploration on the moon and elsewhere. And so geophysics is obviously quite a broad discipline, and so he's focused down on two specific techniques. Here, active source seismology, and you can see some examples in the upper right of astronauts deploying an active source experiment on the moon. And then you can see Ernie doing an active source experiment here in one of his field sites. And then also magnetometry, using a magnetometer to measure the local magnetic field and seeing how it varies as you move around and place to place. And so this was done both on Apollo and we do it here pretty routinely on Earth. And so his project has been broken down into what we can call two separate field areas. The first of these is a planetary science and technology through analog research NASA grant, which we cram this into a nice acronym Gila monster. You can read it there for yourself. But this basically is a field study that's based out of the San Francisco Volcanic Field just north of Flagstaff, Arizona. And the idea here is to add geophysics to one of these NASA desert rat studies, which was a geologically based traverse. And so we have several different approaches, both a mission-based and a terrestrial field seismology-based experiments that we did that Ernie will tell you more about here. And the idea is to study the relationship between the volcanic and tectonic features at depth in this area, and then also talk about how we would do this science on future missions. I'll add that this was a field area that was used to train the Apollo astronauts. So there's a lot of heritage in using this site for this kind of science. His second project is looking at basically the geophysical signature of lava tubes through magnetometry. And this is part of another NASA P-STAR project called TUBEX, which is led by Kelsey Young, who's over at Goddard. And it's situated up in Lava Beds National Monument in Northern California. And then the idea here is there's lava tube structures that we can go and explore into, and then basically use geophysics to try and understand the subsurface structure and extent of that tube ahead of time and develop some strategies for going into these tube interiors and how we would go about doing exploration with these on another planet. And so these are of interest, of course, because they could serve as a place for astronauts to live, or perhaps house pristine samples or create unique environments that would be of interest for exploration. So this is something that's really new and interesting, and Ernie will tell you all about it. And I think the really cool part about Ernie's dissertation is he's very timely. There's a whole bunch of new opportunities for geophysics coming on the horizon, which he maybe tell you about a few of these. But the idea is that the Artemis program is planning to send astronauts back to the moon. I show a picture here of an artist's rendition of what the Artemis astronauts might be doing. The artist chose to basically depict an astronaut doing geophysics, which I thought was fantastic. We also have robots and other spacecraft that are planning to go and potentially do geophysics at that surfaces of the moon. So I think Ernie is well positioned to help inform how these studies should go and give advice and background for where the science and how it should be done on the surface in the most effective way. So I'm looking forward to seeing more and learning about Ernie's defense here. So let's go forward and let Ernie, you can tell us about what you've been up to. So I'll switch it over to Ernie now. Stop sharing. Bring Ernie up. There we go.
Which
floor is yours.
All right, thanks, Nick. I assume that you see the presentation mode, right? You're not seeing my mode. You see the full screen, right?
Yeah, we're seeing the screen.
Okay, great. Great. Well, thanks, Nick, for that. Really appreciate it. Really appreciate everything that you've done for me over all the years. So good afternoon, everyone, and thanks for attending my defense today on my research on the geophysical exploration of terrestrial and lunar volcanic fields. I'd also like to thank my committee for taking the time to be here today. So thanks to everyone. So for my discussion today, I'll first cover a bit of the motivation for my research on terrestrial analogs of the lunar volcanic features with a background on lunar surface exploration. I'll then discuss two traverse style options for studying a field site. The first being as an Apollo style non-geophysically prioritized traverse. The second being a targeted approach to a geophysical problem in the same field site. So I'll follow this with a magnetic study of the lava tubes with application to lunar exploration, and finish with my thoughts on applying lessons from the terrestrial field geophysics that we perform to lunar surface exploration. So first off, what are planetary analogs? Well, on Earth, planetary analogs are locations that provide a representative environment of locations on other planetary bodies. So locations such as Lava Beds National Monument and San Francisco Volcanic Field, they can be used for studies of lava flows, volcanic vents, and lava tubes similar to volcanic features that are found on the moon. But why do we use planetary analogs? Well, we can use them to understand various scientific processes and features such as volcanic fields. We could also use them to assess the ability to find and utilize resources such as volatiles or potentially structural capabilities that may exist at other planetary locations. And then we can also use them to conduct engineering and operational tests prior to conducting similar activities on other planetary surfaces. So each of these three areas can be used to inform the others, and then ultimately they can be used to improve the ability to conduct lunar exploration. So to date, the only experience that we have of humans conducting fieldwork on another planetary body comes from the Apollo missions that went to the moon. During these missions, human surface exploration of the moon consisted of 6 landings between 1969 and 1972. During these missions, they spent about 300 hours of surface time, of which about 80 hours of that was EVA time, or time outside the lander, that included various types of geophysical and geologic studies. So just what is geophysics? Well, geophysics is simply the study of physical processes and properties of a planet using various types of techniques. A variety of these geophysical studies were performed by the Apollo astronauts, which include magnetometry, which you see the portable magnetometer in the upper left, gravimetry, which you see one of the crew members from Apollo 17 performing a gravity measurement in the lower left, and heat flow studies, which you see a heat flow probe installed into the ground from Apollo 17, and also both active and passive seismic studies, which were performed on a number of different of the Apollo missions. So of the various studies that were performed during Apollo, the seismic and magnetic studies are specifically applicable to my research. So during Apollo, a passive seismic array was created through the deployment of seismometers at the landing sites of Apollos 12, 14, 15, and 16. You can see those locations of those on this map on the left here. Results from this array provided an understanding of the various layers of the near and deeper interior of the moon, such as down to 1,000 kilometers by both Kovacs and Watkins in 1973 and Cooper et al. In 1974. And then Weber, 2011, used the same type of data to determine the size and composition of the interior core of the moon. So then also magnetometry was used during the Apollo missions. The surface magnetometry included both stationary and portable units on 4 of the Apollo missions, and this was described by Dial and Gordon in 1973. The results showed magnetic variations across the surface between 40 and 313 nanotesla. Now, for reference, the magnetic field on Earth is between 45,000 and 50,000 nanotesla. So it's significantly smaller. There's significantly smaller magnetic anomalies on the moon than the magnetic field that we see on Earth. But also during these missions, they saw that there were maximum gradients across the landing sites. The Apollo 14 landing site saw gradients as much as 54 nanotesla per kilometer. And the Apollo 16 saw as much as 370 nanotesla per kilometer gradients across their landing sites. So active seismic studies were also performed by the Apollo crews, and these included on Apollo 17, the Lunar Surface Profiling Experiment, which consisted of 4 geophones in an array near the lunar lander. You see those depicted in the upper right here, where the geophones are the blue triangles, and the lander was actually over here at the flag. And it also consisted of 8 explosive packages as the seismic energy sources, which are set at various distances along the lunar rover traverse path. And in the left here, you can see the lunar landing location in the Terrestrial Valley for Apollo 17. And the rover traverse path is denoted as this red line. And the locations where they placed the explosive packages, which were the seismic sources for this experiment, are denoted by the yellow stars. Now, results of this showed a 5-layer seismic profile in the upper 1,000 meters of the subsurface of the Terrestrial Valley. You can see that outlined here. Now, during Apollos 14 and 16, both of these crews conducted a smaller scale active seismic experiment consisting of 3 geophones at 45-meter spacing and a crew operated thumper type device as a seismic source. Here you see one of the crew members holding the thumper as they were deploying the geophones along this line. Now, results of these experiments showed 2 or 3 layer seismic profiles, including a distinct regolith layer within the upper 50 meters or so for both of the landing sites. Now on Earth, we perform similar types of field studies as those conducted by the Apollo astronauts. We perform magnetometry, which you see in the upper left, active and passive seismic studies, 3D laser mapping, which you see Patrick and Sajjad working with here. Also, we take gravity measurements and can perform ground penetrating radar surveys, which you see Nick pulling an antenna for a GPR. There's also a number of other types of geophysical techniques and experiments that are done on the surface, but these are some of the ones just for examples. So how do you apply field geophysics to a lunar analog? Well, as Nick mentioned, one option is to apply a seismic studies to an Apollo-style traverse. In this case, I define an Apollo-style traverse as a rover traverse path that is prioritized for geologic sampling and observations versus any kind of geophysical studies. And it just so happens that NASA performed a simulated mission based on this type of approach in the San Francisco Volcanic Field in northern Arizona in 2010. Now, this picture here is a picture of the conceptual lunar rovers that were used by the crews during this simulation. The field area for this study is the San Francisco Volcanic Field, which is a part of the San Francisco Mountain Volcanic Complex. Now, this area includes cinder cone vents, lava flows, and local and regional fault systems. Our specific field area is a 50 square kilometer region of the San Francisco Volcanic Field, which is centered on the SP crater, which is a cinder cone crater. And that's located here in the center of this geologic map and shown in the picture on the right. And also you can see its associated lava flow. Now, this area provides an excellent analog for lunar volcanic terrain. And historically, this area has been used as a human spaceflight exploration analog, such as during Apollo, this was one of the locations where the crews were provided mission and geologic training. Then in 2010, NASA conducted the simulated human lunar rover mission, where crews spent 2 weeks traversing the area and stopping at various locations called science stations. Now, these locations are designated by the yellow and blue dots on the map. And at these locations, the crews egressed the rovers and conducted geologic sampling and observations. And just however, as a reminder, that there were no geophysical studies performed during the simulation. So the route that the rovers took was defined purely by the geologic objectives to get to the stations for observations and sampling. So for our study, we performed active source geophone line experiments at 19 of the science stations. And the locations for the 19 science stations are noted with a GPH for geophone, followed by the number. And you can see those in the kind of the red and white font throughout the map. Now, each line would be equivalent to an Apollo 14 or 16 style active seismic type of experiment. So each of the 19 geophone lines consisted of sources that produce seismic waves and geophones that detect the resulting seismic motion. The source for our study was a sledgehammer on a metal plate, which is demonstrated here by Don Pettit, who was an astronaut who was able to join us in the field for this research. Now, our lines consisted of 24 geophones at 5-meter increments and 7 to 9 sources at 30-meter increments. And this is shown schematically in the figure with the geophones denoted as blue triangles and the sources as red dots. So what happens is that for each shot, which you see as the red star in this figure, the seismic wave propagates into the ground and is refracted or bent back towards the surface when it encounters a layer of increased velocity. Now, this is depicted by these ray paths that are shown as various colored lines. Now, these waves are then received at each of the geophone locations along the surface, which in this case would be located at each of the tick marks along the upper x-axis. So therefore, each geophone, let's see, get to the next slide. So therefore, each geophone picks up the seismic wave at later times, which is seen in this plot of time, which is on the x-axis, and geophone locations, which is on the y-axis. The arrival times are then selected or picked and are noted in these blue dots as you go along the plots. And these times are the arrival times of the seismic wave at the various geophone positions. Now, for the 19 geophone lines, there were a total of 161 shot locations, which resulted in over 3,800 individual wave traces and potential arrival time picks. Now, these arrival time picks here are plotted here for each of the geophone positions. So in this case, on the x-axis, you have all the various positions of the geophones by distance. And on the y-axis, you see the arrival time that the various seismic waves arrived at those geophones. Now, as you can see, there is a significant amount of heterogeneity in the arrival times across the field area. But despite this, we can use this here to create an average 1D seismic velocity profile for the region, which is shown as the inset of velocity on the x-axis versus depth on the y-axis. So for this study, though, I break this down to analyze each of the individual geophone lines. So for the seismic analysis, I use a Bayesian reversible jump Markov chain Monte Carlo methodology to create an ensemble of seismic velocity layer models, which uses an iterative process. The ensemble consists of a list of possible solutions with similar misfits. So for this analysis, for each iteration of the analysis, it starts with the current velocity model, shown as 1. It then updates the model in one of several ways, which includes adding, removing, changing, or moving a part of the model. And subsequently, the arrival times for the seismic waves at each of the receivers is then calculated based on this new model. And finally, the misfit of the new model is determined with respect to the observed data and is compared to the previous misfit. And then based on this, it's either retained or discarded. So for this analysis, the model was added to the ensemble every 500 iterations, resulting in an ensemble of 2,000 possible 1D velocity profiles for each of the geophone lines out of the 1 million iterations that it was processed through. This results in these 19 1D seismic velocity profiles. And for each of these profiles, the y-axis is in depth to 60 meters, and the x-axis is shown is velocity from 0 to 4,000 meters per second. The mean velocity from the ensemble is in red, and the standard deviation is shown in the dashed black lines. So you have 19 individual 1D profiles at this point. So for the next step, I took the ensembles across all of the locations, which is equal to about 38,000 models for the 19 geophone lines. And I created a histogram of the velocities from these models, which I had binned at 20 meter per second intervals. And then based on the peaks of this histogram, this results in 7 distinct layers, which are seen here as the various peaks from left to right across the histogram. And it has the velocity ranges, which are shown in the upper right. So these 7 geophysically defined velocity layer ranges were then applied to each of the 19 seismic profiles. So you see they basically have colorized the profiles based on the velocity ranges for each of the profiles. Now, based on the geologic observations at these locations, we determined the following interpretations for the 7 layer types. First, there was a low velocity, which are shown here in the red box. And first, the low velocity layer of regolith is followed by a cinder and a fractured lava layers. And then the next layer is interpreted to be a transition from a fractured lava to layers of increasingly consolidated lava. And then finally, the highest velocity layer, which is interpreted to be the country rock. So looking at these 1D velocity profiles, you can see there's significant heterogeneity across the 19 profiles, but there are also some trends and similarities within the geographical groupings. The primary trend is that of a shallow layer of 1 to 3 meters of regolith. So that's this kind of purple layer that you see across the top of a lot of these. In fact, you see it on 16 of the 19 profiles. And then each of these individual groupings, which I've shown at the bottom of the various plots, can be discussed for their own localized interpretation, but I'm going to give just a couple of examples on the next slide. So the 2 examples I'll review are locations B and a pseudo transect or a pseudo line of locations for the profiles. So location B is actually located up here right on the SP cinder cone lava flow itself, which this lava flow is the youngest lava flow in the field area. And as you can see from the profile, it's not yet developed a regolith layer on the surface, and instead has a 13 meter thick fractured lava layer, which is then overlaying a consolidated lava layer. Now, this matches the visual ground truth that we have actually at this location in the field. And then the pseudo transect is made up of 3 science locations. Geophones lines 17 and 18 are essentially co-located, and this happens to align along one of the lava flows, which you can see denoted by this orange line on the geologic map, where lines 17 and 18 are at the south, working their way to the north with geophone line 6. So these profiles show a consistent regolith layer at the surface. You can see across the top. And you also see a fractured lava layer of about 15 meters thickness, denoted by this yellow layer. What you can also see is that as you get partway up this lava flow up to position geophone line 13, a fractured lava layer is overlain by a cinder layer of increasing thicknesses to the north. So this would be the interpretation of this particular lava flow in this particular location. And you could also do this for the other positions that I showed on the previous chart. So some conclusions from this seismic study, which was based on an Apollo-style traverse, include both geophysical and field operational aspects. So from a seismic perspective, we were able to identify 7 discrete seismic layers within the study area. Based on the field observations, we were able to interpret and define each of these layers. And then we are also able to determine the thicknesses of the layers at the various discrete points of the geophone lines, as well as provide an interpretation of these layers along one of the lava flows using multiple. Now, as far as considerations for lunar surface operations, if we can expand the seismic points beyond the single locations performed during Apollo missions, we can have the potential to increase the results from point locations to continuous features or specific structural types, even if not specifically targeted. Now, this provides for assessing the geophysical variability across the field area, which is what we did here in the San Francisco Volcanic Field. And then secondly, there is no guarantee that the optimal positioning of these data points if you're not prioritizing the geophysics. So therefore, this study also highlights the need for traverse planning with an integrated geophysical objectives for the other objectives of the traverse. So now that we've examined adding a seismic study to a non-geophysically prioritized Apollo-style traverse, I'll examine the same field area with a targeted approach to a specific geophysical problem. In this case, we examined the linear alignment of monogenic volcanic vents in the area. And this alignment has been noted previously by Connor et al. In '92 and Conway et al. In '97, where they hypothesized that the vent positions are partially controlled by local faults. So for this study, we again used seismic refraction lines and examined the analysis results for velocity variations that indicate likely fault positions. I'll then review the likely positions of the faults based on their probable strike and relative to the vent locations. So the picture shown here is actually one of the cinder cone vents, which we're looking at in this study. So for this study, we'll again use a 2D seismic refraction inversion analysis to determine the fault locations. Well, I'm sorry, we'll use the seismic refraction inversion analysis, and in this case, it'll be a 2D version of it. The previous studies have used this type of technique, a seismic refraction, to locate faults, which includes the study by Hull et al. 2006, where they created a 46-kilometer-long refraction survey around the San Andreas Fault. And this survey included 912 seismometers at 50-meter intervals and 63 borehole place explosive sources, which produced this 2D velocity structure that you see here. The interpretation of the faults and where they're located is circled in the white dashed circle. And you can see the velocity variation both vertically and horizontally at this position. So for our field site in the San Francisco Volcanic Field, we determined the placement of the seismic refraction lines based on visual alignment of cinder cone vents relative to inferred continuation of mapped faults. So on this map of the field site, the mapped faults are shown in yellow, and with their inferred continuation shown in blue. And this inferred continuation runs beneath the lava flows in this area. So volcanic vents volcanic vents are shown as the dark orange circles. And then we place 1 kilometer long refraction lines, which are shown as red lines on either side of 2 of the volcanic vents. And these nodal lines are placed approximately perpendicular to the average strike of the mapped faults. So each refraction line, which I'll also refer to as nodal lines, consisted of 51 nodes or seismometers, which were placed at 20-meter increments. Let me get those in. And also it consisted of 32 shot locations at 40-meter increments. So here you see a picture that shows some of the nodes, and this is the mechanism we use for the source, which was a 40-kilogram steel cylinder that was accelerated into a metal plate by a large elastomer band. And then here's an example of a cross-sectional view of the placement of the nodes, which are shown as red, and the shot locations, which are shown as yellow in this particular figure. So for the analysis, I applied a 2D version of the Bayesian reversible jump Markov chain Monte Carlo method, which I discussed earlier, to determine 2D seismic velocity profiles of the upper 200 meters beneath the nodal lines. For the analysis, I ran 10,000 iterations with a saving every 100th iteration for an ensemble of 100 models. The velocity structure and the standard deviation plots, which are shown here, velocity and standard deviation plot, for line 1A, let's see. Well, I have them shown here, sorry. And then in the center here of the slide, I've included the map of the locations of the 4 nodal lines. I examined the resulting velocity and standard deviation plots for the locations that are consistent with fault structure, and I've labeled it here as white lines in the velocity profile. I then went through and selected the upper and lower points of each fault location, shown by the red and blue points in the standard deviation plot, for each of the 100 saved ensemble iterations. And then this essentially creates an ensemble of fault location points. So here are the analysis results for the other 3 nodal lines. And as you can see, for nodal line pair 1 on the left, there is a subsurface graben structure that reveals itself, which are, again, by these white fault denoting where these, the white lines denoting where the faults are located. And then in nodal line 2, you see the subsurface structure reveals a horse type feature. And you can see that in both nodal line 2A and nodal line 2B. So I then use the ensembles of the fault location points to calculate the planes and poles for all possible combinations of fault planes between the 2 nodal lines for each of the nodal line pairs. Now the poles and the best fit planes are shown on the StereoNet figures I show here, with the best fit strike and dips noted below each of them. From this, the best fit strike was plotted between the pairs of nodal lines. So the nodal lines are shown as red lines here, with the other colored lines denoting the position in the best fit strike for each of these pairs of fault lines. Now, as you can see, the results show that the faults lie beneath the associated volcanic vents, which you can see here with the volcanic vents outlined in black and the rims outlined in brown. So what you can see is that essentially the vents and the faults do appear to be co-located. So this method of locating subsurface faults could be extended to other planetary locations, such as the Terrestrial Valley, which was the landing site of the Apollo 17 mission. And this would be to study the hypothesized graben structure that is believed to have formed that valley. So here I show a cross-section of the Terrestrial Valley with the relative positions of the Apollo 17 landing and the lunar surface profiling experiment hardware indicated by the yellow stars, orange Y, and the red and blue flag. So for scaling of the San Francisco Volcanic Field nodal lines to the Terrestrial Valley, I used a wavelength ratio between the 2 locations based on the relationship of wavelength, frequency, and velocity. Now this results in a scaling of 8:1, which I conceptually show here by overlaying a cross-section of the San Francisco Volcanic Field nodal line over the Terrestrial Valley. Now from this, you can see that a San Francisco Volcanic Field style linear array, which consists of maybe about 10 more nodes than we had in Arizona, and potentially 5 or so more appropriately sized source locations, could be used to examine the Terrestrial Valley for the graben structure that is hypothesized to be in the area. So in conclusion, for this targeted approach to a study of a geophysical problem in the San Francisco Volcanic Field, there's both the geophysical conclusions and the operational considerations. So first, from a geophysical perspective, I was able to determine the fault planes, which are hypothesized to be contributing factor to the vent locations was able to determine that they align beneath the studied cinder cone vent locations. Also, I showed that the nodal seismic lines of the San Francisco Volcanic Field can be used as an analog to scale from for a similar study on the lunar surface. Now, with respect to the science operations aspect, traverses should include targeting specific geophysical problems to systematically answer larger multidimensional geophysical problems versus non-prioritized geophysical data point locations, such as using the Apollo 17 traverse, but designed to position sources and seismometers in particular locations and array configurations to study the larger 2D structure of the Taurus-Litcher Valley versus the single 1D result that was achieved with the lunar surface profiling experiment. Also, another thing to consider is that for the execution of this type of large-scale study on the lunar surface, I would suggest that similar study would benefit from including crew-assisted robotic operations. Now, what this means is that in the field, we manually did everything. We installed the nodes, manually went to locations and created the shots. But in this case on the moon, I think the crew could be primed for selecting the sensor or data locations, but then once they do so, they would use a robotic type of capability to execute the sensor deployment or conduct the data reading. So I'll switch gears now to using magnetic studies for lava tubes as an analog to performing similar studies on the moon for the next portion of my research. Terrestrial magnetic studies of lava tubes have been limited to detecting and observing lava flows in active lava tubes, which was conducted by Buda and Negro in 1995. And also there was a geophysical study of lava tube structure in the Lava Beds National Monument, which was conducted by the Central Federal Lands Highway Division and authored by Meglich in 2003. This picture that you see here is a picture looking towards the entrance of the inside of Ship Cave, which is one of the lava tube sections which is included in my study. So first off, what are lava tubes? Well, lava tubes are caves of basalt within solidified lava flows that have previously transported molten lava. They form during volcanic eruptions when the surface of a lava flow solidifies and insulates the molten lava, which is in the interior. This molten lava continues to flow, and when it drains, leaves a hollow tube or a cave. So on Earth, these lava tubes can reach tens of meters in diameter, such as Skull Cave shown on the left. Whereas on the moon, lava tubes are theorized to potentially reach hundreds or thousands of meters in diameter based on work by Blair et al. In 2017. And in the right figure here, you can see a collapse pit or a hole into a void suspected to be a lava tube in the Marias Hills region of the moon. Now this hole is 65 meters in diameter and is 80 to 88 meters to the floor of the void. So from the surface of the moon to the floor inside the hole. So there exists a method, there exists a need for a method to locate intact lava tubes without relying on identifying of collapsed portions of tubes or pits. So locating lava tubes on the moon will provide access to study locations which are largely unchanged since they were in place billions of years ago. And it could also provide access to locations to shelter human crews from the extremes of the lunar environment. But some of you might be asking, why do we use magnetics to locate lava tubes? Well, the premise is that the basaltic lava flow is essentially a large magnet and that the lava tube is a hole in it. Thus, the void from the lava tube would result in a reduced magnetic field or a negative anomaly at that particular location. Now on Earth, the Earth's magnetic field increases the magnetic signatures, whereas the moon, on the moon, any magnetic signature is a result purely of remnant magnetism, which is left in the basalt from the lunar magnetic dipole, which ceased several billion years ago. Our field site for this study is Lava Beds National Monument in Northern California. And it consists of 1,000 square kilometers of volcanic features, including over 200 known lava tubes. The specific lava tubes I use in this study are intact segments of the Modoc Crater lava tube system, which is traced in this red line here across the field area. The yellow box depicts, the yellow box encloses the segment containing the intact portions, which are known as incline, skull, and ship caves, which are the three segments I use in this study. Beneath this, you can see pictures for each of their entrances from inside each of the tubes. Now for this study, we captured two types of data sets. The first is ground level magnetic survey over each of the tube segments. And we collected this by walking a magnetometer perpendicular to the longitudinal axis of the caves at 3 to 5 meter increments. 3 to 5 meter intervals. And here you see Kelsey collecting some of this data. Now for this, we ended up hiking on the order of 20 or more kilometers across this field site right here. And you can see this resulted in a highly dense ground level magnetic map of the study area, where the magnetic highs are the warm colors and the magnetic lows are the cool colors, or the blues. You can see that most of the tube sections, which are noted by black outlines, you can see that most of them are overlaid with cooler colors, which denotes a negative magnetic anomaly, which would be expected. So the second data set that was collected was 3D LiDAR laser mapping of the interior of the caves, along with ground level topography. Now here you see Patrick performing one of the scans. Now I use these 3D scans to create magnetic models of the lava tubes. So from the magnetic surveys, I removed the Earth's background field along with the background variation due to the lava flow, and then interpolated the data onto a regularized grid and smoothed the results with a median XY filter. This produced ground level magnetic anomaly figures you see in the left column. Additionally, I modeled each of the lava tubes from the LiDAR scans as a void within a block of basalt with constant magnetic properties. The results are shown here in the right column. The outlines of the tubes is shown in black for each of the figures. Now, as you can see, there are various similarities and differences between the observed and the model data, which I believe the most striking similarity being the negative anomaly, which you see produced by Skull Cave, both in the observed and the modeled. The next step was to relate the ground level magnetic anomalies to the geometry of the lava tubes. For this, he used the model of a cylindrical magnet per the work by Gay in 1965. This model relates the magnetic anomaly, which is the delta F, to the magnetic susceptibility, K, which is and also a constant of the Earth's magnetic field and its inclination at the field site, along with the sealing thickness of the lava tube, and relating its height and width to an apparent radius, R. Now, the first thing I used the relationship for was to determine the apparent magnetic susceptibility for the lava flow at our field site. To do this, I sliced each of the lava tubes, per the schematic, into 1 meter slices along its longitudinal axis and determined the observed strongest negative anomaly, sealing thickness, height, width, and a cross-sectional area for each of the slices. I then binned and plotted this data according to the geometric ratio consisting of cross-sectional area, sealing thickness, and apparent radius with respect to the magnetic anomaly strength. From this, I was able to determine the best fit linear regression line from which I could determine the apparent susceptibility of the lava flow. For this area, it was determined that the susceptibility was 0.155. I then used the overall median negative anomaly for each of the lava tubes, along with the observed median sealing depth and a relationship for the magnetic anomaly produced by the cylinder to calculate an apparent radius for each of the lava tubes. You can see that here with the results in the red numbers. And we can then compare these results to the actual observed median apparent radius, which is the next line down. Now, as you can see, Skull Cave shows the best match between the calculated and the observed apparent radius for the tubes. And this is likely due to the signal to noise ratio, which may likely be related to the ratio of sealing thickness to apparent radius for each of the tubes. So for the next portion of the analysis, I'll use just the apparent radius calculated for Skull Cave. This next portion, I used the gradient of the magnetic anomalies to attempt to estimate the widths of the tubes. To determine the gradients, I used a method that takes the square root of the sum of the squares of the gradients along both the X and Y axis. I did this for both the observed data on the left column and also for the model data shown in the right column. Now, as you can see, the gradients for the model data closely mirror the widths of the tubes, which are outlined in white. However, the observed data only for Skull Cave is this clearly outlined, which you can see here. Whereas for incline and ship, the gradients in the over top of them doesn't really produce the same outline. So for this example, recall that the calculated apparent radius was 9.3 meters for Skull Cave. Assuming a half width of 10 meters based off of the distance between the gradient lines, and a relationship for the apparent radius, I was then able to calculate a half height of 8.6 meters. So you can see that the actual median half width was determined to be 10.6 meters, and the median half height was 7.5 meters. And you can compare those to the calculated numbers. So this shows that this technique can be used for a first order approximation of the internal geometry of the lava tube, assuming that the magnetic properties and the sealing thicknesses can be independently determined. And then finally, I look at using the same relationship to approximate the possible magnetic anomalies produced by a lunar lava tube based on remnant magnetism. So even though the moon's magnetic dynamo ceased billions of years ago, the remnant magnetism still remains. And based on possible strengths of remnant magnetism, we can relate observed collapsed pit sizes to possible strengths of magnetic anomalies that may be produced by the lunar lava tubes. So this plot shows magnetic anomaly on the y-axis and the geometric ratio on the x-axis. Each of the four colored lines represent basalt of varying remnant magnetic properties, which are listed here in the key. Now for this example, I use a known geometry of the Marius Hills hole, which is shown in the photos at the bottom, to define the lava tube sealing thickness, height, and then assume a width based on a 2-to-1 ratio of width to height. These dimensions give Marius Hills hole a geometric ratio, and Marius Hills hole and the lava tube that it's potentially a part of a geometric ratio of 0.57, which you can pick out on the x-axis of the plot. And then it returns a possible magnetic anomaly range from 6 nanotesla to 580 nanotesla, dependent upon the remnant magnetism in the area, all of which of these levels are detectable by current capabilities of magnetometers. So in conclusion, from a geophysical perspective, we have found that magnetic anomalies produced by a lava tube follows magnetic signature of a basic cylindrical model. We also see that the magnetic gradients produced in high magnetic signal to noise ratio environment can be used to reveal the perimeter of the lava tubes, and that the relationship of magnetic anomaly to geometric ratio can be generalized to the moon to predict lunar lava tube anomalies. Now, from a lunar surface science operations perspective, results of the terrestrial lunar analog area surveys can be used to determine minimum data coverage requirements. This can be used by by studying an analysis of the reduced resolution data sets. And also, use of the terrestrial ground survey methods for lunar surface ops should consider use of human robotic partnerships. Now, this could be done to alleviate crews from repetitive data collection operations and could benefit from planetary rovers capable of traversing tens of kilometers per day, which are similar to the distances which we covered to collect the magnetic surveys, but significantly more than is accomplished by the current rovers on other planetary surfaces. So finally here, I want to wrap up with some discussion on some takeaways from terrestrial geophysical fieldwork that can be applied to lunar surface exploration, such as that which you see depicted here in a NASA graphic of a future Artemis astronaut conducting seismic studies. So first of all, what field method does your study need? Well, it can be noted that geophysical fieldwork can generically fall into a few different types of methods. So first, in my opinion, there are point locations. This can be either installation of sensors at a single point, such as a magnetic monitoring station, or conducting a study at a single point, such as a single geophone line. A second method is obtaining multiple data points along a prescribed line or transect, either via multiple repetitive sensor deployments or readings, such as the nodal lines that we executed, or performing collecting GPR data or ground penetrating radar data. And then thirdly, there are area surveys, which can be a variety of patterns that can systematically cover a region at a specified data density, such as the magnetic surveys which we performed on the lava tubes. And then secondly, what mode will your field method use? So along with what method, a determination of what type of mode of execution will need to be determined. For this, I've divided the modes into 4 types of categories, where each assumes there is some amount of mission control oversight from the Earth. The first of these modes are astronaut executed tasks, which are essentially tasks that are manually performed by an astronaut. Now, this would be similar to most of the way that we perform Earth-based geophysical field work, where we're actually out there, hands-on the equipment, and conducting the task. The second mode would be for robotic augmented crew tasks. This is where the crew would use robotic mechanisms to increase the efficiency of the activity. And this could be applied to the installation of multiple seismic nodes along a transect, where the crew is required to select a location, but then they can command a robotic placement of the node. And then a third potential mode would be for crew-assisted robotic operations, so kind of in reverse, where the crew deploys and or retrieves an autonomously operating rover to conduct any of a variety of types of geophysical area surveys. Something like this could be applied to the magnetics surveys, where a rover is set out to perform a prescribed path and then returns back to the crew member or back to the base. And then finally, the final potential mode of operation will be for telerobotically deployed and operated rovers from Earth. And depending on the complexity of the rover, this method could be applied to a variety of operations. This would be similar to the performance of the rovers on Mars that are operating today. And then one final thought. For lunar surface exploration, the combination of field method, operational mode selected, will need to be balanced between the time, complexity, risks, and costs versus the scientific requirements to answer the questions at hand. And these issues can be addressed by first performing similar field studies at lunar analogs on the Earth. So with that, that's the completion of my presentation, with one exception. I do have a number of acknowledgements that I'd like to make, people to point out and such. So obviously goals are never accomplished alone, and I'd like to thank a bunch of folks, which I can't possibly thank everybody right now. So just realize I'm not intentionally leaving anyone out at this point. But I would like to start by thanking the NASA PSARC grant program and the Gila Monster and TUBEX grants and teams for helping me with funding and helping support for my studies and my research over the years. I'd like to thank the Angie Wiley Dissertation Fellowship for support for completing of my dissertation, the Essex Travel Funding for being able to attend any number of conferences. And then also thanks to the UMD Geology Department's faculty, the staff, particularly a few of the folks that I've dealt with regularly, which was Michelle, Dorothy, Joanne, Todd. Their help and guidance was invaluable. And then Nick's Planetary Geophysics groups, I shared a lab with for all these years, to Angela, Conchen, Aaron, Jonathan, Aisha, DK, Fivos, Kira, Ross, and Scott. Thanks to all of you guys for all the help, all the guidance, all the assistance with questions that you've given me over the time. And then committee members, Ved, Monghan, Jess, and Jake, I truly appreciate you guys taking the time today, and also to read my dissertation over the last several days or weeks. I know it's you got plenty of other stuff going on, so thanks a lot for taking the time. And then finally, a couple additional thank yous. One to the Goddard Volcanology and Writing Group, and you guys know who you are. Thanks a lot. We've met every week for years now and learned about volcanoes and helped each other with writing and figures and things. And it was your suggestions are just, I couldn't have made it without you. And then a few folks, Dean, Kelsey, Jacob, Patrick, Brent, and Ryan. I've interacted with you, all of you, over the years, some of you since Desert Rats, and kind of have guided me on this path and helped me when I've had issues, or given me guidance when I've wanted suggestions. And then I want to thank Nick for your guidance, your friendship, and your willingness to provide me with the experiences to be successful in my graduate studies and into the future. And I'd like to thank my mom and dad, Ernie and Mary Bell, who hopefully are still able to be connected right now. Not sure how their internet was doing, but for their support, their encouragement throughout my life to reach for new goals. And Then finally, I'd like to thank my wife and my son, Tanvir and Ethan, for your love, your support, and your patience during this time while I work towards this goal. So thank you. Thanks to all of you, and thanks to many, many others. So with that, I'll be happy to take any questions.
Okay, so if you have a question, please raise your hand and I will call on people as they show up in the chat. And I think I will unmute you for you if you have a question. Go ahead and unmute Laurent.
Ernie, thanks for these great presentations. It was a very nice work what you described here. I have a little bit of a question for application to exploration of the moon. So you were advocating how we can use magnetic anomalies, essentially surveys to find about those underground structures. Now, of course, the magnetic field of the moon at some point vanished, right? So we have only a few regions that have very high magnetizations, and some lava flows are I think, more recent. I mean, depending where, but the youngest Mary basalt seems to be younger, I think, than this time of when there was a high magnetic field. So do you have any advice about, or do you have any idea about how much of a signal we might be still able to find in those places where the newest lava flows on the moon?
Yeah, sure, Laurent. Actually, if I can go back, well, maybe. Sorry, I'm going to try and go back to this one plot. Oops, too far. So you're right. The magnetic dynamo ended a couple billion years ago or so. But the one thing to note is that most of the volcanism was actually also complete by around that time frame. Now there is newer, more recent volcanism like you've talked about, but a large portion of it had already occurred at that point. So places such as Marius Hills and other locations would have had a remnant magnetism that would be left over from the time when they're actually, or I assume that there would be leftover from the time when there was still a remnant magnetism or a magnetic dynamo to create a remnant magnetism in those locations. So you're correct in that regard, but even the lower magnetic locations, which are areas such as, let's see, some of the lower ones, lower basalt, and even the lower remnant magnetisms that may exist in lunar swirls, would result in, even though it's very small anomalies of just maybe tens of nanotesla, assuming that it's above the background noise, it could potentially still show the locations of the tubes and locations where the anomalies would be have like a low anomaly essentially at that location. But sorry, go ahead, Laura.
Would that include places like Remco Mounds where there was this Chinese rover recently?
Yeah, the rover's on the far side of the moon, if I remember right. And I'm not sure how recent that volcanism was. So I'm not completely sure.
Yeah, I was asking the other one, which is on north in the very recent, or trying to get to a recent Murray, where they have a sample return. But that's good. Thanks.
Okay. Yes. Yeah. Sure.
Okay, Dean, I'll unmute you so you can ask your question. He's still not unmuted. Just a sec.
You can leave Dean muted. That's okay.
Oh, jeez.
Sorry about that. Let's try again.
No worries.
When you were back on the San Francisco Volcanic Field seismic stuff, you had a basement unit and you had an estimated seismic velocity for that basement unit. Was that consistent with either the Kaibab sandstone or the limestone or the sandstone that was in there? I didn't get that, and I'm not sure whether the basement there was either the sandstone or the limestone.
Yeah, so I think you're talking about on this plot, Dean.
Yes, sir.
Yeah, so in particular, you're probably looking at these two here, location A.
Yes.
Yeah, so this is the higher velocity, the two profiles of higher velocity, and they're actually co-located. And since you're very familiar with the area, these were on the northern side, basically the northwest corner of SP crater itself. So
Okay.
getting towards where the limestone is exposed. So
Okay.
my estimation is that this is probably the limestone that we're seeing, the kaibab that we're seeing at this point. This is just on this down off the cinders itself, where the SP and the adjacent cone to the west meet. So just coming down there towards the road. So it was most likely the kaibab.
Okay. Thank you. Good
Yep.
job.
Thank you. Good to see you.
All right, Chuck, go ahead and unmute.
Hi, Ernie. Great talk.
Hey,
I
Chuck.
thought that was very interesting. I have a question also about the San Francisco Volcanic Field. So I think the cones along the faults are really an interesting finding. I was wondering if you had any information about whether those faults are syneruptive, like they actually occurred as a result of deformation during the eruption, or do you think they were there before the eruption, maybe long before the eruption occurred? And you know, that might be quite important for understanding if, for example, there might be shallow sills associated with these volcanoes or not. So anyway, if you could speculate about that, it would be great.
Yeah. So you're talking about the faults that I'm showing mapped in the yellow and the blue here, I think, right?
Yes.
Yeah. So that's a good question. I think for the hypothesis to work, I would assume that they were there pre-eruption, and they actually are aiding as a low stress pathway essentially for the magma to the surface. And that would be my hypothesis anyways at this point, that they were there pre-eruption versus the eruption forming the fault. I think that addresses your question.
Okay, thanks.
Yeah, does that answer your question though, Chuck?
Well, I'm not sure it's open and shut.
Yeah, I don't think so either. I think there's work to be done.
I don't want to pursue it now. I think there's an interesting possibility since some of those cones are actually elongate along the fault direction. You know, it's interesting to think that maybe some of that is surface displacement that occurred during intrusions, which localized at the surface of the vent locations, but might be fed by dikes that are, you know, north-south trending.
Yeah, yeah. In fact, the one that we looked at on the right here, this vent 6735 was one of the elongated ones. It's about 2 kilometers long and only 1 wide. So yeah, I understand what you're saying.
Yeah, okay. Anyway, it's interesting. Thanks. Great.
Yeah.
And model.
Thank you.
I'll unmute. Phil, can you unmute yourself or should I unmute you?
I just did it. Thanks. Hey, Ernie, great talk. I enjoyed that very much. The photos are fantastic. As you know, this is not my area of expertise, and I'm going to ask a naive question. What do you assume 10 years from now you're in charge of a program to go to the moon and implement some of the extensions of the analog that you used in parts 1A and 1B? What are the weakest components of that? What would keep you up at night if you were to do that? I'm trying to think of all the problems you might have. And, you know, something simple like coherence of a seismometer with the surface of the moon, for example, would be, in my view, an issue. And of course, I don't do this. What can't you extrapolate from the analogs to the lunar system, for example?
Yeah, so one thing you said there about the coherence of the seismometer to the moon, in other words, just how well it's even connected to the surface. That is an issue because it's the regolith is different than what we see here on Earth. So it's not exactly the same, not exactly one-to-one. They do have experience though of actually installing a few geophones during Apollo, so we'd be able to hopefully rely on some of that type of data and how they did that there. Although they did have an issue on, I can't remember, it was 14 or 16, where one of the geophones did work its way out, and they had to reinstall it partway through the execution of the study. And they weren't quite sure if that was due to the like memory of the cabling, or if that had to do something with the regolith itself that caused it to work its way out. So that wasn't completely sure. So as far as things that we want to make sure that they look at and that we cover, and that might not be as easy to cover from analogs here on Earth. Well, that's a good question. Let me think for a second. So one would be just making sure you have, like I said, the proper hardware. So if you're going to use a larger scale experiment, you're going to want to use hardware that provides seismic waves appropriately. So if it's explosives, are they appropriately sized for the actual medium that it's going to be going through on the moon versus the medium that we see here on Earth? So we want to make sure we make those calculations appropriately. The hardware, yeah, you want to make sure it's connected appropriately to the surface as well. Otherwise, we simply wouldn't get the readings. But then also just making sure it survives the environment, which I know we have a lot of experience with the space environment, but the lunar surface is a little bit different. So there's maybe the regolith itself could cause some issues or something to that effect. I don't know that. I'd have to think about your question a little bit more, though. I'd want to think about your question a little bit more and just get back to you probably with a little bit more specific type of answer.
Thanks very much.
Yeah. Any other questions? Does Dean have another question there, it looks like, or?
I think his hand's just
nope.
Okay.
His hand's still just up. Chuck, did you have another one, or did you take your hand down and put it back?
Sure, I'll ask another question.
Okay.
It's a stimulating talk. I'll shift to the magnetics. I thought your model was quite excellent. I was intrigued by the, you got great fits over part of the area and kind of poor fits in other areas, especially with the positive anomalies on the north side of, can't remember what it's called, Skull Cave or something like that. Yeah. Now, and when I guess I have a comment. When I look at that, I think that these basalts probably carry very high remnant magnetizations as well. I mean, I know you modeled the apparent susceptibility, which is fine, but it could be that some significant rotation occurs after these basalts pass through the Curie point.
Mm-hmm.
And so maybe those sort of dipoles in individual cells are actually rotated. And you might want to try an inversion where you try just the geometry that you've got, and then just allow the dipoles to rotate. And you might find a really interesting thing about the cave if that is a result of rotation and deformation, after the tube was formed and material was sort of sagging around and cooling at the same time. Anyway,
yeah,
it's just a thought about.
Sounds like you're talking about Skull Cave here, particularly with this large anomaly.
Yeah.
Mm-hmm. That's one of the areas of question that we have as far as. So that would be something to look at. What you're just saying is that was that the cause of essentially the increasing anomaly that we see there.
Yeah. So if if your geometry is fixed because your LiDAR data is great,
mm-hmm.
then all you've got left is rotation of the vector of magnetization.
Mm-hmm.
And, you can't do that with susceptibility, but if it's high remnant magnetization, no problem. You can rotate it.
Yep.
And maybe that's telling you something about the structure of the cave.
Okay, a good point. Something to look at in the future. And thanks.
Okay, are there any more questions out there for Ernie? All right. Last call. All right, well, thank you so much, everybody, for attending. Really appreciate everybody spending time with us this afternoon to hear Ernie talk about his research. We will now adjourn to the private part of the defense. So everybody have a great day, and hopefully we'll run into each other at a conference here soon or in the department. All right. Okay.
Great.
Bye, everybody.
Thanks, everyone. Appreciate it. Have a great day.